It is coming. It doesn't care about politics. It doesn't care about the economy. It cannot be bargained with. It is simply math. Imagine a specific moment in time. Tuesday, January 19th, 2038. It's early morning in Europe, late night in the Americas. At exactly 3:14 and 07 seconds Coordinated Universal Time, the world takes a breath. 1 second passes, and then chaos. In an instant, computers across the globe, millions of them, don't just stop working, they hallucinate. They travel back in time. Traffic lights in major cities might freeze or revert to default modes. Database servers managing pensions and mortgages could suddenly calculate that you haven't been born yet. Radar systems could lose track of objects. It sounds like the plot of a bad science fiction movie, or perhaps a retread of the Y2K panic that everyone laughs about today. But this is not Y2K. Y2K was a formatting error, a lazy habit of using 2 digits instead of 4. It was a software problem. What faces us in 2038 is much deeper. It is a fundamental limit of the physical reality we have built our digital world upon. It is called the year 2038 problem, or the Apocalypse. And to understand why this date is a ticking time bomb, we have to talk about something seemingly unrelated: a Korean pop star and a French rocket. Let's start with the pop star. Do you remember Gangnam Style? In 2012, Psy's viral hit broke the internet. Literally. It was the first video in history to surpass 2 billion views on YouTube. Google, the owner of YouTube, had problems. They had built their view counter using a 32-bit signed integer. In plain English, that means the maximum number of views the counter could physically hold was 2,147,483,647. When Gangnam Style hit that number, the counter didn't just roll over to 0. It threatened to break the code. Google engineers had to scramble to upgrade the variable to a 64-bit integer, which can hold a number so large it would take more than the age of the universe to count to it. That was a funny, harmless glitch. It was just a view count. But what happens when that same math error happens to a $370 million rocket carrying 4 satellites? June 4th, 1996, the European Space Agency launches the Ariane 5 rocket. It is the pride of European engineering. 37 seconds after liftoff, the rocket flips 90 degrees and disintegrates in a massive fireball. Why? It wasn't a loose screw. It wasn't a fuel leak. It was an integer overflow. The software from the older Ariane 4 rocket was reused for the Ariane 5, but the Ariane 5 was faster. The horizontal velocity value became too high for the 16-bit variable that was holding it. The number hit the ceiling, and just like an odometer in an old car, it flipped. The computer interpreted this flipped number not as speed, but as a command to correct the flight path. It steered the rocket into its own doom. That crash is considered one of the most expensive software bugs in history, and it happened because a number got too big for its container. Now, take that concept, that integer overflow, and apply it not to a view count and not to a rocket speed, but to time itself. This brings us to the heart of the 2038 problem. How does a computer know what time it is? It doesn't look at a wristwatch. It doesn't look at the sun. It counts seconds. In the early days of computing, specifically in the development of the Unix operating system at Bell Labs in the late 1960s, engineers needed a standard way to mark time. They decided to start a clock. They called it the Epoch. The starting line was set at 0 hours, 0 minutes, and 0 seconds UTC on January 1st, 1970. Every second that ticks by, the computer adds 1 to that counter. So, if your computer says it is 50 seconds past midnight on January 1st, 1970, the internal number is just 50. Today, as you are listening to this, that number is somewhere around 1.7 billion. It's a big number, but it fits comfortably inside the standard container used by most legacy systems, the signed 32-bit integer. We need to get slightly technical for just 30 seconds, but stay with me because this explains the doom. A 32-bit system has 32 switches, zeros or ones. That gives us roughly 4.2 billion combinations. However, because computers need to represent time before 1970, they use one of those bits to indicate positive or negative. This cuts the maximum positive capacity in half. So, the magic number, the ceiling of our digital reality, is 2,147,483,647. On January 19, 2038, at 3 hours, 14 minutes, and 7 seconds, the Unix clock will hit that number. At 3 hours, 14 minutes, and 8 seconds, the counter will try to add one more. But there is no room. The binary code will flip from all ones to a 1, followed by all zeros. In a signed integer system, this specific sequence signifies the lowest possible negative number. So, instantaneously, the computer will not think it is 2038. It will think it is Friday, December 13th, 1901. Let that sink in. 1901. Your bank software calculates interest based on time duration. If you put money in the bank in 2037 and the computer thinks it is now 1901, you have a negative time duration of 136 years. Does the algorithm delete your account? Does it charge you a century of overdraft fees? Or does the entire banking core freeze because negative time is an impossible variable that the programmers never wrote a catch block for? You might be sitting there looking at your MacBook or your Windows 11 gaming PC and thinking, I'm fine. I have a 64-bit processor. And you're right. Most personal devices, smartphones, and modern servers manufactured in the last decade run on 64-bit architecture. They can count time until the heat death of the universe. If the world was only made of iPhones and gaming PCs, we would be safe. But the world is not made of consumer electronics. The world is held together by invisible, ugly, old technology. This is where the fear truly lies. It's not the laptop on your desk. It's the computer inside the concrete wall of the hydroelectric dam. It's the embedded controller inside the anti-lock braking system of a truck manufactured in 2015. It's the routing hardware buried under the Atlantic Ocean. These are called embedded systems. They're the silent workers of civilization. They were designed to do one thing perfectly, cheaply, and forever. They run on 32-bit chips because 32-bit chips are cheap and reliable. They're often soldered onto circuit boards that cannot be removed. They run software that hasn't been updated since the 1990s because the company that wrote the code went bankrupt 20 years ago. Let's look at a terrifying example of what happens when time breaks in a military context. On February 25, 1991, during Operation Desert Storm, an American Patriot missile battery failed to intercept an incoming Scud missile. The Scud struck a barracks in Dhahran, Saudi Arabia, killing 28 soldiers and injuring nearly 100 others. The investigation revealed the cause, a time calculation error. The Patriot's internal clock measured time in tenths of a second, but stored it in a 24-bit register. The longer the system stayed on, the more the tiny rounding error drifted. After 100 hours of continuous operation, the internal clock was off by 0.34 seconds. 0.34 seconds doesn't sound like much, but a Scud missile travels at Mach 5. In 0.34 seconds, it travels over half a kilometer. The Patriot missile looked for the threat in the wrong place. It swung at empty air. The math failed and 28 people died. That was a tiny drift error. The 2038 problem is not a drift. It is a total reset. Imagine the GPS constellation. While the satellites themselves are constantly updated, the ground receivers, the millions of industrial GPS trackers on shipping containers, in agricultural combines, in old aircraft navigation systems, Many of these are 32-bit legacy hardware. If they reset to 1901, they don't just lose the date, they lose their position. The GPS algorithm requires precise time to calculate location. If the time is wrong, the location is wrong. We're talking about supply chains breaking. We're talking about power grids that rely on precise frequency timing synchronization desynchronizing. When grid nodes lose sync, safety breakers trip to prevent physical damage to the generators. If enough breakers trip at once, you get a cascade failure, a blackout. So, why isn't this on the news every night? Why aren't we seeing the same panic we saw in 1999? Part of the reason is human psychology. 2038 feels far away. It feels like someone else's problem. In 1999, the deadline was months away. We could see it. 2038 is still over a decade out. Corporate executives operate on quarterly cycles, not decadal ones. No CEO wants to spend $10 million today to fix a router that might break after they have already retired. But there is another reason, a more dangerous reason. We have become complacent because Y2K didn't end the world. We look back at Y2K as a joke, a false alarm. But the only reason Y2K didn't destroy the economy is that thousands of engineers worked sleepless nights for years to patch the code. We survived because we prepared, not because the threat was fake. But fixing Y2K was relatively easy. It was software. You could rewrite the code. Fixing the 2038 problem in embedded systems is a hardware nightmare. You cannot patch a chip that is sealed inside a concrete pillar. You have to dig it out and replace it. And this is where the scale of the problem shifts from a computer science puzzle to a logistical nightmare. Think about the sheer number of microcontrollers that surround you. A modern car has up to 100 electronic control units. A commercial airplane has thousands. An oil refinery has tens of thousands. We have spent the last 40 years sprinkling silicon dust over every aspect of our existence. We buried sensors in the ocean floor to monitor tsunamis. We embedded chips in the foundations of bridges to measure stress. We launched satellites that are now drifting in graveyards, orbits, but still transmitting signals. Many of these devices are what we call install and forget. They were installed in 1998, 2005, or 2012 by engineers who have since retired or passed away. The documentation is gone. The source code is lost on a floppy disk in a landfill somewhere. But the device is still there, ticking, counting seconds, waiting for 2038. This creates a phenomenon known as zombie infrastructure. These systems work perfectly fine today, so nobody touches them. If it ain't broke, don't fix it, is the mantra of infrastructure. But in 2038, they will all break at once. Consider the file systems. Your data isn't just floating in the ether, it lives on hard drives formatted with specific rules. Many older Linux servers use a file system called X3. X3 uses 32-bit timestamps. Even if you upgrade the computer processor to 64-bit, if you mount an old hard drive formatted in X3 and try to write a file with a date past 2038, it will fail. It will corrupt the data. This means we don't just have to replace chips, we have to migrate petabytes of archived data, medical records, legal history, government archives, to new formats. It is digital archaeology on a planetary scale. But there is a glimmer of hope. The guardians of the internet are fighting back. And the front line of this war is the Linux kernel. The internet runs on Linux. The cloud is Linux. Your Android phone is Linux. So fixing the Linux kernel is priority number one. For years, the Linux community, led by developers like Ariane Bergman, has been waging a quiet war against the variable known as time_t. This is the specific line of code that defines time as a 32-bit integer. It was a monumental task. They had to comb through millions of lines of code, identifying every single instance where the kernel looked at a clock, and rewrite it to be 64-bit compatible, all without breaking the compatibility for the old 32-bit programs that still need to run. In 2020, with the release of Linux kernel 5.6, they largely declared victory. The software layer of the open source world is now ready for 2038. But this victory comes with a massive asterisk. Just because the kernel is fixed doesn't mean the device is fixed. A vendor who sells a cheap smart fridge or a router might grab the free Linux kernel, but run it on a cheap 32-bit processor to save 50 cents on manufacturing costs. If the hardware can't handle the 64-bit number, the software fix is useless. We're still manufacturing future e-waste today. Every 32-bit device sold in 2025 is a ticking time bomb for 2038. And then there's the problem of the bridge. Imagine a modern 64-bit system trying to talk to an old 32-bit database. The modern system sends a date, February 2040. The old system receives it, panics, and translates it to 1904. It sends back a confirmation for 1904. The modern system receives 1,904 inches and rejects it as an error. The transaction fails. This interoperability crisis is where the real danger lies. The global financial system is a mesh of new and old. High-frequency trading algorithms running on supercomputers still have to interface with banking mainframes written in COBOL in the 1970s. Speaking of COBOL, we face a human resource crisis. Who is going to fix this? The code that runs the foundational layers of our banking and utility grids was written in languages that universities stopped teaching decades ago. The graybeards, the generation of programmers who built the internet, are leaving the workforce. We are handing over the machine to a new generation that doesn't fully understand how the engine was built. We are forgetting the secrets of our own technology. So, what is the worst-case scenario? It's unlikely to be a Hollywood-style apocalypse where planes fall out of the sky. Critical safety systems usually have mechanical fail-safes. If the computer crashes, the brakes still work physically. The real threat is a digital depression, a grinding halt of economic activity. Imagine a week where credit card readers stop working, where supply chain logistics software freezes, leaving supermarkets empty, where pension funds cannot disperse payments because the database says the recipients haven't retired yet. It creates a cascade of mistrust. If you can't trust the timestamp on a digital contract, you can't enforce the contract. If you can't trust the logs of a server, you can't audit a company. The invisible glue of trust that holds the global economy together is digital time. If time breaks, trust breaks. There's also the salami slicing effect. We won't strictly wait until 2038 to see problems. We will see them sooner. In fact, we already have. In 2006, AOL server software crashed because it was programmed to look 32 years into the future to calculate timeouts. 2006 plus 32 is 2038. They hit the wall early. As we get closer to the date, any system that projects into the future, mortgages, 30 years, bonds, long-term contracts, will start failing one by one. The cracks will appear before the dam breaks. So, is there a solution? Yes. But it requires something that humans are notoriously bad at: long-term thinking and spending money on invisible prevention. We need a global audit of critical infrastructure. Governments need to mandate that critical systems, energy, water, transport, finance, must be 2038 compliant by 2030. We need to treat this not as an IT ticket, but as a national security priority. But perhaps the most important takeaway from the year 2038 problem isn't technical, it's philosophical. We tend to think of the digital world as ethereal, perfect, and eternal. We think of the cloud as a place where data lives forever. But the year 2038 problem reminds us that the digital world is shockingly physical. It is made of silicon, copper, and electricity, and it is bound by the laws of mathematics and the short-sighted decisions of humans. We built a digital skyscraper on a foundation meant for a bungalow. We assumed that the code we wrote in the 70s would be replaced by now. We were wrong. The temporary solutions became permanent infrastructure. January 19th, 2038 is a mirror. It forces us to look at the fragility of the civilization we have built. It asks us a question. Are we good ancestors? Are we building systems that will serve the future, or are we leaving time bombs for our children to defuse? The clock is ticking. We have roughly 400 million seconds left. It sounds like a lot, but in the world of engineering, that is practically tomorrow. Let's hope that when the clock strikes 3 hours, 14 minutes, and 7 seconds, the world keeps turning, and the only thing that crashes is the party we throw to celebrate fixing it. If you want to understand more about the invisible systems that run our world and how easily they can break, make sure you are subscribed. We dive into the deep end of technology, history, and the future every single week. Don't let your time run out. I'll see you in the next one.